Is this the right one? I think so. All right. Let's go back to this. We'll do it this way. What is that? Okay, nothing important. All right. So good morning. Welcome to our last lecture in the first week of Calc 2. Today we're going to kind of round off those week 1 topics, which were U sub, areas between curves, and average value. So the one that we still need to talk about is average value. But I'd also be happy to solve a few problems of any of the other varieties too, just to make sure we have a well-rounded experience. And I'd like to begin with anything that you guys have been struggling with in the homework. So we should all be into, God, I'm a mess. We should all be into WebAssign at this point. Even if you haven't bought an access code, remember you can get in there. Just when you are asked for your access code, scroll down until you see the option to enroll with temporary access. Oh, my hair tie broke. So go ahead and take a look at your homework so far and see if there are any particular problems that you would like to see worked out. And then you can type those problem numbers into the chat, and we will begin with those. I will be right back. Yes, I will. I don't even know where to begin. Okay. So let's see what we got here. Looks like we'd maybe like to take a look at number 14. Okay. 5, 14, 19. I think that's a good enough start. What was 5? Let's start there. This is homework 1, problem 5. And let me write it down. Integral 0 to 1. And we'll just do a few of these. 5, 7, 19, 14. Okay. Number 7 is actually very similar to a problem that we did in lecture on Wednesday. So if you want to see number 7, I would suggest going back and rewatching the video that I posted from our lecture on Wednesday. But I will go ahead and do number 5 and numbers 14 and 19. So let me switch over the dot cam here. Here is number 5. They're asking us to evaluate this integral. It's a definite integral going from 0 to 1. And the integrand, the thing inside, is the square root of 1 plus 7x dx. If this was just the square root of x, then that would be a power rule problem. And I could just evaluate it using the power rule. As is, note, square root of 1 plus 7x is not equal to the square root of 1 plus the square root of 7x. We can't begin this way.
I believe it's a cube root in the problem. I could be wrong though.
Oh, okay.
Yeah, it is a cube root.
WebAssign randomizes some things, so this might be one of those things that is randomized and came up different for me than for you, but oh no, mine is also a cube root. Okay. But the same issue is present, right? Cube roots, roots in general, powers in general, do not play nice with addition or subtraction, so we can't split this up. That's not going to work. And that sort of shit is a surprisingly common mistake in Calc 2. Please don't do it, right? Square roots, cube roots, they never, ever, ever distribute. But what will work is a little substitution. So the substitution we want to make here is for the stuff under the root. Because if all I had was the root of my variable, then I could handle that as a power rule thing. So what will work here is if we make the substitution, i.e. we let, and I'm going to use the variable z again because I don't like to use u's for this. Substitute for the radicand, substitute for the thing under the radical. So if z is equal to 1 plus 7x, then dz is just 7 dx. And also, because this is a definite integral, I need to change my bounds. When x is equal to 0, that means z is going to be 1 plus 7 times 0, which is 1. So when x is equal to 0, z is equal to 1. And so my new lower bound, my old lower bound was 0, my new lower bound will be 1. And then to find my new upper bound, I plug my old upper bound into this expression. So when x is equal to 1, what is z? Well, z would be 1 plus 7 times 1, which is 8. And remember, in Calc 2, you must do this. It is not optional. You must change your bounds when you make a substitution in an integral. So this box here now has everything I need in order to make my substitution go through. According to that box, my integral is equal to the integral from 1 to 8 of the cube root of z. And then what is dx? Well, I don't have dx equals some stuff here. I have dz equals 7 dx, but that implies that 1/7 dz is equal to dx. So this dx I'm going to replace by 1/7 dz. Does everybody see that? So now that 1/7, this is being multiplied, right? That's how the differential works, multiplies the integrand. So that 1/7 is a multiplicative constant. It will come out of the integral. And I have 1/7 times the integral from 1 to 8 of the cube root of z dz. And now that there's no addition or subtraction or anything like that going on underneath the cube root, I can just write it as z to the power of 1/3. So this is 1/7 times the integral from 1 to 8 of z raised to the 1/3 power dz, and that's an easy integral to evaluate. It's easy to find an antiderivative there because it's just a power function. So I add 1 to the power. 1 plus 1/3 is 4/3. My 1/7 will come along for the ride, and I get z raised to the 4/3 divided by 4/3 evaluated from 1 to 8. And the magic of having changed our bounds is that we don't need to go back to the old variable. We can just evaluate this new expression in terms of the new variable between the new bounds. So I'm going to plug in 8, and then I'm going to plug in 1. First, dividing by 4/3 is the same as multiplying by 3/4, and that is a constant. It can come out of this evaluation step. So I will have 1/7 times 3/4 times z to the 4/3 evaluated from 1 to 8. just making my life a little bit easier. So then I continue. The 1/7 times 3/4, that's 3/28. And then when I evaluate z to the 4/3 between 8 and 1, this is 8 to the 4/3 minus 1 to the 4/3. 1 to the 4/3 is just 1, but 8 to the 4/3 we can clean up. That's the cube root of 8 raised to the power of 4. The cube root of 8 is 2. So that's the same as 2 to the 4, which is 16. So this is 3/28 times 16 minus 1. In other words, this is 3/28 times 15. Now, is there any simplification that we can do there? The numerator has factors 3, 3, and 5. The denominator has factors 2, 2, and 7. So there's no cancellation that can be done there. If you want to, you can write this as 45/28. And then last time, there were a few questions about what sort of simplification would I require from you on a test. If you left it like this and didn't proceed to here, I would be inclined to maybe dock a half point, something like that. We do need to be comfortable evaluating expressions like 8 to the 4/3, and we should know that 1 raised to any constant power is going to be 1. So stuff like that is stuff that I will expect of you. It's not stuff that I will penalize you for harshly, but it is the sort of thing that we should, as Calc 2 students, be comfy. Distributing the 3/28 is fine. Yeah, I prefer to pull all the constants out that I can. That way I don't have to mess around with the fractions any more than I need to, right? Like if I left the 3/4 in there, then I would have some fractions and maybe need a common denominator and maybe need to mess around with that a little bit before I could get to my answer. But no, there's nothing wrong with leaving the 3/4 or even the full 3/28 inside. No harm there. I'm just lazy. Any other questions on this one? So the two important things to recall when you're working on a substitution problem, first is that you need to get every little bit of your integral in terms of the new variable. That means there can't be any x's or dx's. If there are still any x's or dx's left over, then you can't do your integration step, right? You cannot find an antiderivative of a function of two variables or a function of z times dx. That shit just don't work. You'll talk about that stuff in Calc 3. It requires some headier ways of thinking. It is not at all obvious. And you cannot treat one variable like a constant or anything like that. So get everything in terms of the new variable and remember to change your bounds. That's it.
The one mistake I made with this problem is for z, I plugged in 1 plus 7x. And then like when I was, for some reason, when I changed the bounds, I was doing 1 plus 7 times 8. So I was getting like a really weird number.
Yeah, so you used the new bounds, but you went back to the old variable.
Right.
The nice thing about changing the bounds is that you don't need to go back to the old variable. So at this step, you can just go ahead and evaluate. There's no need to plug back in the 1 plus 7x for z. That's an understandable mistake, especially if your Calc 1 teacher let you do some combination of the two things. And that's okay. Just remember moving forwards that new variable, new bounds, you don't, once you've gotten to this step, you never need to see an x again. You do everything in terms of the new variable. That's a good comment. Are there any other questions or comments on this one? Okay. So we wanted to see 5, 9, 14. What else was it? I don't think we'll do all of these because some of them were similar. 7 was similar to a problem that we did in class the other day, right? So we're not going to do 7 here. We just did 5. We wanted to see 14 and 19. So let me take a look at those. Yeah, again, if you wanted to see number 7, this is a good problem. The trick is going to be to substitute for this piece, the 1 over x cubed piece, and then the 1 over x to the 4 is going to be a part of your differential. So I would rewrite this as e raised to the power of 1 over x cubed times 1 over x to the 4 times dx, and then substitute for the highlighted piece here. And if you want to see the details of this problem, watch the video from Wednesday. I think it was the last or second to last example that we did on Wednesday. Was 9 requested? Wasn't? No, okay, 9 is a fun problem, but we'll jump to 14, which was this area problem. Let me get it copied down here. It says find the shaded area. And they give us a graph. Just to give a quick sketch of this. One of them looks like this, and the other one looks like this. We're told this is y equals 7e to the x. We're told this is y equals x times 7 times x times e to the x squared. And we want to find the shaded area. So coming back to the dot cam, this is what we want to do. We can maybe take a quick look at number 16. So what do we need to do in order to pull this off? Here I'm given two curves, and in both of them, y is expressed as a function of x. So I can treat this as a dx integral, right, where I subtract
the top from the bottom.
Yeah, good, right? So I'm going to integrate the upper function minus the lower function. From where to where?
0 to 170.
Yeah, well, from 0 to whatever the x value is at this point, right? So I need to find the x value where these two curves intersect. By inspection.
They give it to us. So.
Oh, did they give it to you? Oh, they.
Yeah.
So nice. 1, 7e. Yeah. Okay.
But if they didn't, then we just set them equal to each other, right?
Right.
Okay.
Yeah. Had they not given you the x value at that point, you would set the two expressions equal to each other, and you would be able to solve for x there. It's not a super simple equation to solve, actually. So I'm glad that they gave it to us. So yeah. So the game here, the area is going to be the integral from 0 to 1 of the upper function minus the lower function. And we're going to do the integral dx, because we're in this case where we can think of the upper and lower. So we're in the y equals a function of x case. There's no like switching places. They only touch at that one point, and that point happens to be the end point that I care about for my region. So I don't need to worry about splitting the integral up or doing anything fancy like that. So this integral is going to be equal to the integral from 0 to 1 of my upper function is 7 times e to the x, and my lower function is 7 times x times e to the x squared. And remember, we talked about notation a little bit last time. Notation is important in Calc 1, but it's crucial in Calc 2. You need to have good notation. In particular, I'm thinking of these parentheses, these big parentheses that I'm putting around my integrand. Because my integrand is made up of two pieces which are being subtracted, I really do need those parens, because this dx is really multiplying both of them. What that means is that in order to do the substitution, which is necessary to find an antiderivative for the second piece, for this piece, I need to first split the integral up. So let me continue this down here. And the ... ellipses notation is a very convenient way to continue an equation elsewhere on the page. I strongly encourage you to use it. I will treat this as the integral from 0 to 1 of 7e to the x dx minus the integral from 0 to 1 of 7x e to the x squared. dx. So I'm going to do the two pieces separately. Why? Because this first piece is easy. I don't need any substitutions or weirdness. I know the antiderivative for e to the x. This second piece, I do need to make a substitution. And if I make that substitution here, I don't want to make it here. So I can't do it in this setting. I need to split it up first. And this is just using good notation. So you need to write things down in a way that someone can read your shit and understand it. This is how you do that. The first piece is, like I said, is simple. The 7 pops out. And then your antiderivative for e to the x is just e to the x. And he will be evaluated from 0 to 1. The second piece, I'm going to make a substitution. I'm going to let z be x squared. And then dz is 2x dx. I'm letting z be x squared because I've got this e to the x squared business there. And if that was just e to the x or something like that, I would know what to do. That would be easy to handle. So I want to make the exponent for e to the stuff as nice as possible. Also, I have this x lingering here, which will allow me to absorb the 2x dx differential. So if you want to, you could say this means 1/2 dz is equal to x dx. So the x dx piece I will be replacing by 1/2 dz. I also need to change my bounds. When x is equal to 0, z is x squared will also be 0. When x is equal to 1, z is 1 squared will also be 1. Oh, so my bounds don't change, but I still need to go through that. And so this becomes minus integral 0 to 1, 7, and then this x dx, that's going to be gone from my differential, so the x isn't going to be there. But I'll still have the e to the x squared, that's e to the z. And then x dx is 1/2 dz. And depending on how much practice you have with these sort of substitutions, you may or may not want to rewrite the integral one other time as 7 e to the x squared times x dx. So you can see that the x dx really just does turn into this 1/2 dz. A lot of people wonder, where does the x go? It was absorbed by this differential term. Everything else is straightforward. The 7 and 1/2 can come together. Everything here is just being multiplied, and I can pop a 7/2 out of the integral. So this first guy, I'll continue writing him like he is. I won't evaluate him yet, just to keep everything nice and clean. Minus a 7/2 will come out of the second piece here. And I'll be left with the integral from 0 to 1 of e to the z dz. Any questions about how we got to this point? Okay. So then moving right along, antiderivative for e to the z is not difficult. It's e to the z. And we're evaluating from 0 to 1. So this is what I get after I've done all the antiderivative work. So this first piece is 7 times e to the 1 minus e to the 0 minus the second piece is 7/2 times e to the 1 minus e to the 0. And e to the 0, of course, is 1. So this is 7e minus 7 minus 7/2 e plus 7/2, distributing that negative. And now we can combine our like terms. I'll finish this up here. I've got 7e minus 7/2 e. 7e is the same as 14/2 e. And when I subtract 14 halves e minus 7 halves e, I get 7 halves e. And then my constant terms are minus 7 plus 7 halves. So that's minus 14 halves plus 7 halves is a minus 7 halves. So this is what we get. If you're feeling fancy, you can factor the 7 halves out. And that is done. Again, if you want to know like what sort of simplification is required and what sort of simplification is expected, you must get to here. You got to be able to tell me that e to the 0 is 1. You got to be able to tell me that e to the 1 is e. And then I would be happy with either of these answers. But this is the absolute minimum. Questions on this guy, or comments, thoughts, anything? Not too bad, right? The integration here isn't too bad. We got to remember the setup, and then we got a little u sub in one of the integrals. Any questions on that u sub? Yeah, it's interesting. So that's why we had to split them up, right? I only needed to make the substitution in the integral that had the e to the x squared piece. I don't need to substitute to do this. So having a z here and an x here, it is a little bit wonky, but it's important that we have those two different variables because the substitution is only made in the one integral, not made in the other. I agree that this step down here looks a little bit funny, doesn't it? Where you've got e to the x from 0 to 1 and then e to the z from 0 to 1. But the distinction is meaningful. The distinction is meaningful. So this is more just kind of getting used to notation and getting comfy with notation. And you will get there, I promise. It's like so many other things, like skateboarding or hula hooping feels weird and awkward at first, but then over time feels like the most natural thing in the world. Other questions or comments on this? Okay. Oh, I guess just for the purposes of the notes, this was homework 1, problem number, what was it? 14. So if you're rewatching this later, that's what we just did. All right, we wanted to see, I think, a couple others, right? 19 and 17 were both requested. 17 looks interesting. 19, this is another one that we actually did in class. So again, if you want to see 19, go back to Wednesday's video. You can find the link to the video in the same announcement where you find the link to the live lecture. I'll always update those announcements with links to the video as soon as I get them processed on YouTube. This is like the shape like this that we found the area of in class. It's either this one, it's one of these two on the left for the graph to figure out exactly which one you're going to have to find these intersection points by setting the equations equal to each other. But it's a hyperbola, something looking like 2 over x, and then two linear functions, one having slope 1/8 and one having slope 8. Just at a glance, it looks to me like it's probably this guy. And then to find that area, you're going to integrate, so your upper and lower, I'm putting my cursor right now where the upper and lower divide is. So right here at x equals 2, it seems, is where the divide is. The linear function, 8x, is the upper, and the linear function 1/8x is the lower, until you get to x equals 2. And that's when the hyperbola, 2 over x, becomes the upper. So when you set this up, you're going to need two integrals. You're going to have one integral from 0 to this intersection point, where you've got this linear as the upper and this linear as the lower. And then past the intersection point, you'll have the hyperbola as the upper and the second linear as the lower. So again, go look at the examples from the end of class on Wednesday if you want to see this problem solved. 17 was the other one that was requested. So let's take a look at him. We have not done one quite like this yet. So here they're drawing in a little Riemann rectangle for you. I did that once in class when we did our dy version, just to kind of help us out. I'll write it down and then switch back to the dot cam. Find
Professor, I think they asked for 16, no 17.
16? I think I saw both, maybe. Let me see. So 16 was the most recent ask. Oh, 14, 19, 16. Yeah, okay, sorry. 17 wasn't requested. Yeah, 16. Okay. So 16, coming back a little further. Oh, this is a little bit easier. That's okay. So we want to sketch and find the area bounded by y equals x squared minus 3x and y equals 4x. So here we go. We're going to treat this like it's not a WebAssign problem. And I strongly encourage you to do what I'm doing here, and that is graph these things by hand, right? Don't just look at the pictures in WebAssign and try to pick the right one and then set it up. Draw the picture by hand. It's going to make a world of difference, especially in the stuff we're doing next week where we're finding volumes. So get into the habit now. How do I graph these functions? X squared minus 3x and y equals 4x. Well, x squared minus 3x, that's a quadratic, so its graph will be a parabola. The lead coefficient is 1, which is positive, so it's going to be opening up. And if I factor that, that's the same as y equals x times x minus 3. So I know that he's going to have a root here at 0. He'll have a root over here at 1, 2, 3. And then y equals 4x. Well, here, let's finish our graph of this first guy. The vertex isn't super important. It's going to be halfway between there, somewhere down here. So he'll look something like this. Modulo my bad arc. Y equals 4x is a line with slope 4. So I'm going to draw it in looking something like this, just so I can fit it. Okay. So this is the area that we're trying to find, which means I need to find these intersection points. One of them is fairly obvious, the origin. The other one is less obvious. I don't really care what the vertex is down here. Doesn't matter the exact y coordinate there. But we've got this picture. So I want to find this area. That's my task. And the way to do that is to integrate the upper minus the lower from whatever this point's x value is to whatever this point's x value is. I think it's fairly obvious that these two curves intersect at the origin. This has y-intercept 0, so it goes through the origin. This has a factor of x in it, so it goes through the origin. But then finding the other one is going to require solving a quadratic. So to find intersection points, we solve the equation x squared minus 3x equals 4x. All right, I just set those two guys equal to each other. That is equivalent to saying x squared minus 7x equals 0. So that's x times x minus 7 equals 0. So the intersections occur when x equals 0 and x equals 7. right? In other words, the x coordinate at this point is 7. This is 7 comma something. And I don't give a shit what that something is because I only need the x value because I'm only using that point to tell me the limits of integration. This point down here is, of course, the origin 0 comma 0. Okay, so this is our setup. This is the picture that we're working with, and we now have all the information we need to set up our integral. So the area is the integral from 0 to 7 of the upper minus the lower, and it's a dx integral. I want to take a second here because we're still dealing with material that's simple enough to do this. Say, notice that I'm not just writing like mathematical expressions. I'm also writing words. I'm drawing pictures. I've got like these mnemonics in here. Your work should look like my work. As you do your work, try to mimic the way I solve these problems. I know it might sound condescending or shitty or annoying for me to say that. I promise I'm not talking down to you. What I'm trying to do is get you into the good habits now because they will be 100% necessary later. When we get into the really tough shit in this class, it's the words that's going to matter. That's what's going to make things go. So being able to write logically in a way that allows you to go back and kind of think through it, allows your reader to think through it with you, is going to be hugely important because the middle third of this class, that convergence section, is all about logic. It's actually very little about algebra or computation. There will be algebra and computation in there, but the most important stuff is that. So try to make your solutions mimic my solutions. Write in some words. Make sure you explain what you're doing. Use logical connectors like this if and only if symbol. Draw big pictures, all these things. Try to mimic what I do here. Just use good notation. All right, so what is my upper function? It's y equals 4x. My lower function is x squared minus 3x, and I'm going to put that in parentheses because I'm subtracting him as a chunk, which means this negative is going to need to be distributed. If I don't distribute that negative, things will go wrong. And I still have my differential term here, dx. That is the same as the integral from 0 to 7 of 4x minus x squared plus 3x. So that's 7x minus x squared dx. And since that is a polynomial, its antiderivative is easy to conjure. We use the power rule. This will be equal to 7x squared over 2 minus x cubed over 3, all evaluated from 0 to 7. Okay, so the bulk of the work is done here. All the calculus is done here. Are there any questions getting from the start to where we are now?
Is it necessary to write the part where you said upper minus lower?
Necessary. Well, it's kind of a matter of taste, right? So that's kind of why I'm saying like I encourage you or I really want you. No, it's not necessary, but I do advise something like that. So imagine that somebody is going to read your work and that person hasn't been to our class. You want that person, as long as they're a reasonably sharp person that has the background that you all have, to be able to follow it. So if we went straight from here to this integral, would somebody else who hasn't been here to our class be able to understand why? That's the level of detail I would encourage you to write in your solutions. Is enough so that someone who hasn't done this problem knows where all that shit is coming from. So while I certainly wouldn't take off points if you didn't write that, of course not, that would be horrible. I would never do that to you. I do still want to encourage you to do it because it's just good. Think of it as mathematical hygiene, right? Like it's keeping things clean and making sure that they're still understandable. But I wouldn't take off points for it. I do still encourage you to do it.
All right.
Any other questions or comments? This is a good time in the semester to talk about notation because the mathematics itself is still quite manageable. Any other notation questions or like what's expected of you questions, that sort of thing? I'm glad. Okay. All right, so let's go ahead and finish the job here. Both of these are equal to 0 when you plug in 0, so there's not going to be any contribution from the lower limit. But when I plug in the upper limit of 7, I get 7 times 7 squared over 2 minus 7 cubed over 3. And both of those have a numerator of 7 cubed, right? 7 times 7 squared is 7 cubed. And I can factor that out. So this is 7 cubed times 1/2 minus 1/3. I don't know what 7 cubed is off the top of my head. It's 49 times 7. I don't really care. But 1/2 minus 1/3, that's 1/6. So this is 7 cubed over 6. And then if we want to, we can compute 49 times 7 or 7 cubed. Do I have it here? No. Oh, without my virtual TI-83, it's useful from time to time. All right, so what is 7 cubed? 343. So this is 343 over 6. And then just remember that since we're talking about an area, that would be units squared or square units. But I don't require you to write that because we don't have a particular unit of length that we're playing with here. So any last questions on this fella? So Simon asked if I prefer Windows XP. Now, Windows XP hasn't been supported for a long damn time, which means if I ran that on my machine, I would be vulnerable to a lot of nasty stuff. This is Windows 7, which also just stopped being supported. I'm being irresponsible by running it, but I have all of the visual settings turned down to their absolute minimum. Because I used to try to game a little bit on this laptop and I didn't want to waste the very limited video card resources on the operating system. So this is Windows 7 just with all the fancy shit turned off. I will be changing this to some Linux distribution here in the next few weeks because Windows 7 was recently no longer supported. If you have any suggestions for an operating system, I would love to hear them. I'm leaning towards Linux Mint right now. I've used Ubuntu and Fedora in the past, but I'm not sure. It does look cool. Yeah, I like how simple it looks. I'm a big fan of simplicity. Okay. So what do we want to do from here? I know there were a couple other problems that were requested. Let me look and make sure. Linux is almost all used to. I was like, hey, problems is Windows 10. Yeah, Windows 10 would be the obvious answer. I'm just cheap. I don't want to spend money. So I'm leaning towards a free alternative. 14 and 19 were requested also, and make sure that I'm not being silly. Yeah, 10, I don't like my operating system to consume a lot of resources. And Windows 10 is getting up there in its resource consumption. I would never fuck with Windows 8 because it's horrible. I like to have legit copies of software these days. I'm old enough, but yeah, is it like Reddit's R software swap or something like that? No, if you want to send me any information about yeah, about that sort of stuff, feel free to email me. So let's send it to my Gmail, which is this. All right, so same as my Santa Fe email address, just at gmail.com instead of at sfcollege.edu. So we're not having those conversations through the official channels. But let's get back on task. So if there aren't any other homework problems that we desperately want to look at, then I would like to move from talking about areas between curves to talking about these last few things, average value. And then maybe if there's time, we'll even be able to introduce next week's material. Oh, this is going to work. There we go. All right, all right. Yeah, gig of RAM isn't too much. I actually have 16 gigs in this laptop, but it's an old laptop. I'm still debating what to do. I think usually before I retire a laptop, I spend a year or two running some Linux distribution to just play around and see what's up in the Linux community. So this one's getting close to the end of its life. I think it's nearing its Ubuntu phase, but we'll see. So let's begin section 6.5 now, which is the last section we're going to cover this week, and it's on average value. So I'm going to try to motivate this in a way that's tied to some real life stuff, because most applications of the concept of average value are not purely mathematical. Most of them have to do with something going on in the real world. Imagine I gave you a function that told you your speed along a journey. So imagine you set off on a drive. At time t equals 0. The function v of t records your speed. Let's call it your velocity. There is a small difference between the two. T seconds after leaving. Can you find the average speed or velocity for your trip? So, v of 0 is necessarily 0, right? The second I start off, I'm not going anywhere yet, but maybe I speed up and I speed up and I speed up, and it's something like linear like this, but then I like get on the highway and my speed kind of levels off here at 70 miles an hour, and I stay at 70 for a while, but then I hit some traffic and it goes down, and then maybe it comes back up, and maybe I'm speeding for a minute because I got this nice long section of highway where there's no one around, and then I get to my destination, pull off the exit ramp, maneuver around town for a minute, and then I come to a stop. Right, so this is the v of t axis, and this is the t axis. And this is my velocity, my speed during that trip. So maybe right around here, something like 60, 65. Maybe I get up to a maximum speed of like 70, something like this. This is a probable graph for a short trip like that. We know that there is an idea of average speed. I know that in my head, intuitively, I could say, oh yeah, well, for most of this trip, I was going like 60 miles an hour, but for part of it, I was going less, and for part of it, I was going more. And so I have some idea of what my average speed should be, and maybe it should be around 60, but I'm not sure. Is there a mathematical way to say for sure exactly what that average is? If I only went a few speeds, if there were like 3 exact speeds and I was able to start my car and go immediately to that speed, and then immediately to the next speed, and then immediately to the next speed, if this was a discrete set rather than a continuous set, then I know how to find an average for a discrete set. You just add up all the things and then you divide by the number of things. But here there's infinitely many y values. There's infinitely many speeds that I took. Right? For some time here, I was going like 20 miles an hour. For some time here, I was going like 55. For some time here, I was going like 70, 75. And there's infinitely many numbers there. So how do I find the average of those things? Well, it turns out, I'll say here, a equals 0 is this x value. and we'll just call this x value over here where I stop b, then the average value for my velocity function is, it comes very similarly to the way you would think of an average of a set of regular numbers. If I take a set of regular numbers, just like 5 or 6 numbers, and I want to find their average, you add up all those numbers and then you divide by the number of numbers, right? Well, the challenge here is that I've got an infinite number of numbers to add up. If you've taken some physics, you've probably seen, or if you remember this part of Calc 1 especially well, that an integral is actually a way of adding up a bunch of shit. It's an infinite sum. It's how you add up a bunch of values over a continuous set. So here the notation I would use, since my function is v, I would refer to this average value as v_av, and it is 1 over b minus a times the integral from a to b of v of t dt. In other words, it's the area under that curve divided by the length of the interval. So you can think of the area under the curve, or this integral, as like adding up all the numbers in your set. And you can think of this 1 over b minus a as dividing by the number of numbers. From a measure theoretic standpoint, this is the same thing. It is, yeah, it's true. The area under the graph is, well, the area under the graph of the velocity is the displacement. So what we're doing here is we're dividing the displacement by the time. It's a distance divided by a time, right? Which is a speed. And that speed is the overall distance traveled divided by the amount of time it took me to do the traveling. So in this case, it's the total distance traveled divided by the time it took to travel. And if there's any concept of an average velocity, it should be that, right? It should be how far did you go divided by how long did it take you to get there. It happens to be the case that precisely for the reason that, and I should give you some love for that. Yeah, Dalton pointed out that displacement here is the area under the curve of velocity. And so if there's anything that should be an average velocity, it should be how far did I go divided by how long did it take me to get there. And I can interpret that as the integral of the velocity divided by the length of the interval over which I integrated. Now here's the good news. This example from physics generalizes really well. You can talk about the average value of any function, and it will always follow this formula. You won't always have this analogy because not every function is measuring a velocity, so its integral isn't always a distance. But for any function f of x, we'll say continuous on the interval a, b. This is our definition. We can define the average value of the function as, we use that same notation f_av, and it's a constant, right? This is just a number. It's 1 over b minus a times the integral from a to b of f of x dx. Average value of the function on the interval a, b. Right, this is the average value for f of x as x runs over the interval a to b. So this is your definition, and the homework problems that you have just ask you to make these computations. But I wanted to show you the connection to physics there. I think it's a neat thing. The 1 over b minus a, that's dividing by the time. So displacement is the distance traveled, as long as you never go backwards, as long as your velocity is always positive. And then the 1 over b minus a, the b minus a is in parentheses there, right? It's the same as dividing that displacement by the time, right? And so distance divided by time, that should be average speed. But in general, this is the idea. So this is your definition that you're going to need for those homework problems. And if you go on to take any advanced statistics, this is how you find the average of an infinite set that is coming from a continuous function. I want to talk about one other thing. There's one other interpretation of average value. So that's the definition. The average value of the function f on the interval ab. So here's f of x. Here's a, here's b. It's the unique constant function that bounds the same area from a to b that f does. So here, this total area is like that. To get that same area, I think f av is going to be something like this. So the area that's bounded underneath f av, this rectangle, is the same as the total area underneath f. But f av is a constant. So this is the unique constant function which bounds the same area as f over the interval AB, which can be useful in more settings than just the physics setting. We won't see many of them in this class, but when it comes to doing things like finding center of mass for a three-dimensional object, there's a three-dimensional analog to this that's very useful. And especially in statistics, when you have a continuous random variable whose distribution is coming from a continuous distribution function, finding the average of those random outputs is done this way also. This isn't something we're going to spend really any more time in class talking about, but it's one of those little enrichment topics, and it gives me an excuse to have you do some more integrals while we're kind of warming up to the integral section. So as you're doing the homework, remember this definition. This is important. This interpretation will be useful to you if you go on and study any higher statistics. And of course, in physics, the concept of average speed is meaningful, and you see the connection with calculus there in that first example. So we can work one or two little examples here. And let me grab some good ones rather than just making them up off the top of my head. I don't think the textbook is especially rich this section, but that's okay. And then we can use the remaining time today to introduce the volume problems that we'll be looking at. Average value. This will give me an excuse. To do one or two little integrals like this, that's boring. Let's do this. Let's find the average value of the function g of x equals x over the square root of 3 plus x squared on the interval 1 to 3. So this is really just a formula thing. We're going to use the formula above and crunch out the integral. So g av here, I should say, because my function is g, is 1 over b minus a times the integral from a to b of g of x dx. That's what the formula says. So here a is 1 and b is 3, so that's 1 over 2 times the integral from 1 to 3 of x over the square root of 3 plus x squared dx. This little thing with the square roots, by the way, you might want to consider doing this, putting a little tail at the end of the check mark thing there to show you where the square root ends. Not super important for this, but it's a great way to tell your reader what is and what is not inside the square root. Okay, how do I do this integral? Good, yep. Yeah, Nas and Thomas more precisely. We're going to substitute, and we're going to substitute for the thing under the square root downstairs. I've got my x upstairs, which I'll be able to use to absorb the necessary term from the differential. So let's do it. So we're going to do this by letting, and I may need some more space here, that's okay. So I'll let z be 3 plus x squared. Then dz, I differentiate here, 3 differentiates to 0, x squared differentiates to 2x. So dz is 2x dx. This is a definite integral, so I also need to change my bounds. When x is equal to 1, the z is equal to 3 plus 1 squared, that's 4. Oh, sorry, z equals 4. And when x is equal to 3, z is equal to 1 plus 3 squared, 3 plus 3 squared, which is 3 plus 9, right? Yeah, which is 12. So there's all the stuff I need to make my substitution go. And under that substitution, my integral becomes, I've still got that 1/2, still got my integral, but now it runs from 4 to 12 instead of from 1 to 3. My x dx upstairs, x times dx, is the same as 1/2 dz. So I'll have another copy of 1/2 coming from the differential. And then my 1 over the square root of 3 plus x squared, that's 1 over z. 1 over the square root of, 1 over the square root of z. So this is what I get when I implement that substitution. Sorry, this check should, I guess, go down a little further. Yeah, like that. Any questions about how we arrive at this integral?
So I'm a person who tries to think in like generalized steps. So it's for most of these integrals, I'm just seeing what you find the substitution term and then set it up to create new bounds. And then depending on what it is you're solving for, generally apply a antiderivative.
In between those, so after I choose the substitution term and before I start messing with the bounds, I always compute this differential. So the general procedure here is choose what to substitute for, compute the differential, and then see if you can find a way to plug these things into the integral. If not, then you're going to have to go back and try a different substitution. Like if I didn't have this x up here to absorb this x right here, I would be in trouble. So after you compute your differential, first pick the substitution, then compute the differential, then do a little mental check and see, okay, am I going to be able to make that go? Well, here I've got the 1 over the square root, that's my 1 over root z, but can I do anything with this x dx? Well, here I've got 2x dx equal to dz, so I see, oh, okay, so I'm just going to have a 1/2, and then I'll be able to replace those two things together with dz. Then I change the bounds, and then I move to my antiderivative step. But yeah, that's good. So the general procedure for 5.5 stuff, substitution stuff in general, pick your substitution, compute your differential. Then make sure that you can plug those things in. Make sure that you can actually transform the whole integral from x stuff into z stuff. You do that check usually mentally, usually pretty quickly. And then go ahead and compute your bounds, and then write down the new integral and do the antiderivative steps. So my next move here would look like 1/4 integral from 4 to 12, and I'll take a look at the chat there in just a second, z to the negative 1/2 dz. And let's see what's going on in the chat. Wouldn't the inside of the integral be 2 times 1 over the square root of z? No. So the x dx isn't equal to 2's dz, it's equal to 1/2 dz. So there is a little step here that I haven't written down that sometimes I do. Say since dz is equal to 2x dx, and I generally won't write this step down. I'm hoping that we get comfy with these substitutions. Then dz over 2 is equal to x dx. So the x dx here, this circled piece here, gets replaced by dz over 2, or 1/2 times dz. So that's this 1/2 and this dz. And then the 1 over square root z part is correct. Yeah, he just comes along. Comfy? Okay, Lucas, yeah, I've barely checked my email this morning, so I will take a look and see if I've got anything there afterwards, after the office hour, which follows this. So let's go ahead and finish the integral. I've got g av is equal to 1/4 times the integral of z to the negative 1/2. When I antiderive z to the negative 1/2, I'm going to use the power rule. So I'll add 1 to that power and then divide by that new power. Negative 1/2 plus 1 is positive 1/2. So that's z to the 1/2, and then I'm going to divide by 1/2. And that's my antiderivative, so he gets evaluated from 4 to 12. Dividing by 1/2 is the same as multiplying by 2, so I can pop that out. So that's the same as 1/4 times 2 times z to the 1/2 from 4 to 12. And the 1/4 and 2 will come together to make a 1/2. And then when I evaluate this, this is the square root of 12 minus the square root of 4, which is 1/2 times the square root of 12. 12 is 3 times 4 minus square root of 4, Square root of 4 is, of course, 2, and the square root of 3 times 4 is 2 times the square root of 3. So this is 1/2 times 2 root 3 minus 2. And I would factor the 2 and cancel it with the 1/2. Do I dare to round answers? No. Nope, I want exact values. Give me just exact values in terms of the square root, please. So I would not round this. I don't want decimals. In mathematics, we want exact values only, please. So what I would do here is then factor the 2, cancel with the 1/2, and write this as this, which is just this. There may be some problems in WebAssign where they ask you for a decimal number rounded to this or that place. But as a general rule, the problems I'll do my best to give you will be ones where we just want exact answers, either in terms of logs or square roots or trig functions or whatever. If it's not a nice number that we can sort out, then, oh, well, 12 is 3 times 4. Yeah, that's all. So the square root of 12 is the same as the square root of 3 times 4 because 3 times 4 is 12. And then I can take the square root of each separately. The square root of 4 is 2, that's this 2. And the square root of 3 is just the square root of 3. I leave him, leave him as he is. That's okay. It is a decimal. I mean, the square root of 3 is a weird decimal number. But that decimal number is only ever going to be an approximation to the value of that square root because it's an irrational number. And for that reason, we really do want to leave it as a square root. And we need to be comfy doing simplifications like that. This is one of the things that some Calc 1 professors are good at training you on and some Calc 1 professors aren't. But again, in this class, the standards of rigor that we have are such that we really do want exact answers. We don't want to be leaning on the calculator at all. In fact, you should have very few uses for your calculator all semester. If I had square root of 12 over 2 minus 1. Nope, that's fine, Rakib, that's correct. The square root of 12 over 2, though, can be simplified and should be simplified. So I would please try to do that. So the question was, is this correct? And the answer is yes, but we should simplify. So the square root of 12 is, again, maybe if I write it with the 4 first, it's the square root of 4 times 3, because 12 is 4 times 3. And then that's the same as the square root of 4 times the square root of 3, all over 2 minus 1. And the square root of 4 is 2, so that's 2 root 3 over 2 minus 1, cancel the 2's, and you get the root 3 minus 1. And that's the nice way to write this. Again, that's not the sort of thing I'm going to come after you for and like take off a bunch of points, but like a half point or something like that. My general philosophy on this is if you're correct, you're correct. If you answer the question correctly within the parameters that I give you, meaning you give the exact answer in terms of square roots, but it's not as simplified as it could be, then I usually won't take off any points. However, if there's some major simplification or cancellation that can occur that you miss because you didn't simplify the thing that you should know how to simplify, then I would take off like a half point. That's my general philosophy there. So I don't like the idea of pushing people through this class that aren't comfortable doing these sort of simplifications. These should be things that come very naturally to us at this point. But if they don't, please don't panic. I'm not here to penalize you for that. I'm here to teach you calculus. And as long as you learn the calculus, you will be okay. But you should also learn how to do this shit because this is stuff that we make our 1033 students do. It's something that as people who are card carrying, passers of Calc 2 you should be comfy doing. But we'll get there, and no, this wouldn't be something I would take off any points for on its own. This answer would be given full credit, but then I would have a comment like this on the side, and if not doing this affected anything later in the problem, then I would take points off. Any other questions on this guy? Okay, so I want to take the next few minutes here, just these last few minutes of class, and introduce to you the ideas that we're going to be playing with in next week's homework. There is one other topic from 6.5 called the mean value theorem for integrals. It's cool stuff, but it's not really in the same line of thinking that we're talking about right now, so I'll discuss that with you later. You won't have any homework on it or anything like that. I want to get you ready for the volume problems that are coming. Sorry, some really delicious looking food was just placed in front of me. So intro to sections, I think there are 6.3 and 6.4, which are on volume. Volume is a measure, right? It's something that we measure, and it is a measure of like size that we use for objects which are three-dimensional. I am pretty sure that these are some sort of delicious treat. Here they are. Be jelly. That would be jelly. Oh my god. Yeah, these are like s'mores with, I don't know. God damn. All right. Staying on task. Volume. Volume is a measure. No cannabis in them. They were delivered by I don't know, doorstop or something like that. We want to be able to find volumes using integrals, but we don't have integrals that can handle multiple dimensions. Our integrals are really one-dimensional integrals. It's just a dx there, not a dx times dy or dx times dz. So the way we get around this is by thinking of some solid as being made up of little slices. So imagine I have a little cylinder here, right? One way that I can come to understand the volume of this cylinder is by thinking of it as living along some axis. Sorry, my art is bad and I feel bad. Is that meant to be like that? Yeah, it is. Okay. Let me call this axis the x-axis. I can imagine, and I'll call this right here x equals 0, this point right where my cylinder starts. Imagine looking some distance down the cylinder and taking a little slice. And this slice has an area. So imagine putting an axis through the solid. Then take a dx thickness slice. So the thickness of this little slice I've taken here is dx. Some tiny little thickness slice. At each point here along that axis, there's an area. So I'm doing this at say just x, right? The slice is taken at x and is of thickness dx, then that area of the cross section of the slice, I call that A of x, the slice at x. So A of 0 would be the area at this end. Does that make sense? If this thing is 3 units long, then right here would be like the area if I sliced here would be A of 1, the area if I sliced here would be A of 2, and the area at the very end would be like A of 3. I can find the total volume by adding up all the little volumes. Which come from my slices. So let me take that little slice there and just look at it. Here it is. Here's my little slice. This thickness is still dx, and this area is A of x. Then the little volume of my slice is, the idea is that by taking dx to be so very, very small, I can assume that even if the edges of my original solid aren't perfectly flat, I can assume that the edges of my slice are flat. I'm taking them to be so small that even if this isn't perfectly flat, it's very, very, very close to what I would get if it was perfectly flat. I call this little volume dv, right? D for differential. Just like dx is a little distance in x, dv is a little volume. dv will be that little area, A of x, times dx. Which means that my whole volume is going to be the integral from, wherever to wherever. Maybe instead of calling this x equals 0, I'll call it x equals a. And down here, I'll call this x equals b. So that my solid goes from x equaling a to x equaling b. Then my total volume will be the integral from a to b of dv. I'm adding up all the little volumes. And that's equal to the integral from a to b of a of x times dx. So this is the basic idea that we're going to start playing around with next week. This method is called the method of slicing, and the whole game is about finding this function a of x. You can have a more complicated solid than this. Here, if this is actually just a cylinder, then a of x would be constant, right? Because it doesn't matter where I slice, I would always get a slice that looks like that, and it would always have the same radius and the same thickness. But if I had something like a cone, then that would be growing as you went out one direction and shrinking as you go the other direction. The same thing would still work great. So you can find volumes of a lot of solids this way. This is called the method of slicing, and it has some special cases that are called the disc washer method. And we will play around with those first, and then we're going to look at another approach to the volume problem, which has a similar feel to it, but instead of looking at slices, we look at layers, and that's called the onion method or the method of cylindrical shells. So this is where we're going, and I think this is probably a good place for us to end. I don't want to lose you in this yet. So please stay focused on the homework. If you haven't done the homework yet, please get in there and complete it. That is due on Monday, remember. And you want to keep up with the homework, especially at the beginning part of the class. It's really important that you stay up with us. That way you don't fall behind early. That can be catastrophic. So please continue working on the homework. If you've not been able to get into WebAssign, you need to talk to me today, and we need to figure that shit out because we need you in there and getting that stuff done. You want to have that first homework all the way done on Monday. If it's not all the way done, don't panic. You can submit an extension request and I will grant it. But please do really try hard to get all that homework done by Monday, okay? So this is where I'm going to stop the meeting for today. I do have an office hour right after this. So if you've got any particular problems that you want to talk about or look at, I would be happy to do that. Just exit this meeting and then go into our Canvas page and click on the link there to enter the office hour meeting. One last request before we leave, if everybody could just type the word "here" in chat, that way I can keep track of the attendance. So please type "here" in chat. Oh my God, that looks amazing. And that way I'll be able to keep up with the attendance in class. And once you've done that, you're welcome to sign out. And if you want to, I will meet you in the office hour, okay? Any questions? Of course. Alrighty, I think that's everybody having signed in. So I'm going to go ahead and end the meeting. I hope you guys have a lovely weekend. And if you want to talk to me, remember, just go over to the office hour. So that's the link to that is on our Canvas homepage. I will get that fired up here in just a second.